So my name is Amir. I'm with Anybody Technology. I'm the host of today's webcast, and I'm very happy to announce that we have Lauranne Sins today from ETS Montreal, and she will present a study she worked on over the last couple of years. So the outline for today's webcast, I will start a little bit to introduce or to explain who is anybody and what is anybody. Then after a couple of minutes I will hand over the microphone and the screen to Lauranne, and she will present a paper called, or study she has performed over the last years, called a musculoskeletal shoulder model using force-dependent kinematics to evaluate non-conforming total shoulder arthroplasty. At the end we're going to have a questions and answers session, so we will live answer some questions for you. That means if you have any questions during the presentation, you have a little questions box. You see that here, here a little screenshot of that. So you can type in your questions. So whenever you have a question, please type it in. There's the option then that one of my colleagues, so the panelists, will answer something immediately, or then we will postpone it to the end so that either Lauranne or I can answer those questions live for you. There's also, we're going to record this webcast, so we're going to put it on our YouTube channel. So if you miss something, if you have questions, you can of course ask us via email, or you can just then go to our YouTube channel and listen to it again. We will also provide a PDF of this presentation, or more likely of Lauranne's presentation, and we will also make that available to you. So if you miss something, you can reread it again afterwards. Before I start now, I just wanted to mention we had a webcast in September about total knee arthroplasty, and another one also end of September then about total hip replacements, and we're very happy to announce that both of those are now available as publications, as papers. Here are the links. I can also provide you later on with the links to those papers by email. So we are very happy that what has been presented here within this webcast, within these seminars, that this is also available now as a full paper, journal paper. So very briefly, who is anybody? So there's Anybody Technology, that's where I'm working. That's a company based in Aalborg, Denmark. We have also an office in Boston in the US, a little bit outside of Boston. And we develop the Anybody modeling system, and we provide licenses, training, support, and consultancy project around the Anybody modeling system, which is a tool for mostly for biomechanics. We also have several research groups, so in different universities which are close partners or do close cooperation with us. So we have those Anybody research group all over the world, in the US, in Denmark of course, and in Germany. Anybody is used in several different areas. So if you start here on the top left-hand side, you see it's used in work environment and to develop assistive devices. So basically, if a subject has to carry heavy loads, you can analyze those tasks and see what is the most, or what is the best way for the worker to do that. Or then if you want to develop an assistive device like this skeleton type thing here that you see, you can use Anybody to optimize or to develop this device. It is also used for product design and optimization. That can be a wheelchair, as shown here in this picture, but it can also be all sort of products, consumer products that are in close connection with the human being, like a bicycle or many other sports equipment, like an automotive seat, or everything in terms of package design. It can also be in the orthopedic area, or in defense, or in airspace. That brings me to the next point. So it's also used for ergonomic analysis and documentation. For example, if you want to analyze ingress, egress into a car or out of a car, or different ergonomic aspects of shifting the gears or braking or pulling the handbrake. More related to what we're talking about today. So anybody can also be used for surgical planning, evaluation, or failure analysis. So just the surgeries itself, or then in combination with implants. So later on we're going to talk about shoulder implants, but here you see also spinal implants, or in the lower extremities as well. And then anybody can also provide physiological load cases for FE, so for finite element analysis. So here you see, for example, a little demo, so finite element picture of a total hip replacement, which was loaded according to the muscle configuration out of anybody. So anybody does, as I said before, musculoskeletal simulation. That means we use as input the activity and the motion. We applied it to our body model. The body model has bones, joints, muscles, and ligaments. And then we get as output muscle forces, muscle activities, power, many other measures. And we get also for joints, forces, moments, so in general joint loads. This principle is called inverse dynamics. So that means, once again, input is motion, output is forces, so internal forces. This input can come, as you see here in this picture, it can come from recorded motion, like from a motion capture system. There are marker-based systems like Vicon, Qualisys, Simi, but it can also be from inertia systems like Xsense, Animazoo, for example. If you don't have a recorded motion, you can also create the motion yourself by defining joint angles or by defining certain trajectories of segments, for example. So you can define the motion as well. If you have external forces like ground reaction forces recorded, you can use that. Makes it a lot easier. If you don't have that, you can have the Anybody modeling system predict ground reaction forces or forces to the environment, for example. As I said before, output is then muscle forces, muscle activation, so everything what's going on within the human being. Here in this middle animation you see those red and blue bars or lines, so that's basically the force in the muscle. So here are only four muscles of the tibia basically, and here you see then the forces, how they act during a gait cycle. On the right hand side, here you see a screenshot of the full body model. Just to give you an overview, we have roughly 1,200 muscle fascicles in this system right now, or in this full body model. We have a very detailed foot model, we have different knee models, hip, we have very detailed lumbar spine model, and certain areas as well. So today we're going to talk a little bit more about the shoulder model. So a simulation usually runs, you take an activity, so basically an activity of daily living or a certain motion, and you analyze it in the Anybody modeling system. You can do it also more advanced, so you can use patient-specific or subject-specific information like bone geometries from CT scans or MRI scans. So basically you can hook it up with a system like Mimics or Simpleware, and then we can export all the loads for each segments into a finite element model. So we have interfaces to Abacus, ANSYS, and something more generic. If you have an environment, so basically what I mentioned before, sports equipment, automotive environment or anything, there's also the chance to import it directly from your CAD systems. So there's a SolidWorks to Anybody translator. And there's also, of course, some more scripting hook, so you can hook up the Anybody modeling system with advanced scripting languages like Python or some other optimization software, for example. So I think that's enough about Anybody right now. So I'm very happy that we have Lauranne with us today. So she received a diploma in mechanical and plastics engineering in Strasbourg, France in 2009. Then she moved on to Canada, to Montreal, to the ETS, École de Technologie Supérieure. She received a master's degree in engineering, in biomedical engineering there in 2011, and then worked from 2011 to 2014 on her PhD project. And just recently she received, she defended her her PhD successfully, and I'm very happy to welcome Lauranne now. She will present a musculoskeletal shoulder model using force-dependent kinematics to evaluate non-conforming total shoulder arthroplasty. So Lauranne, I'm going to make you presenter now, and okay, we can see your screen now, and I think we can hear you as well.
Okay, perfect. Hello everybody. Thank you, Emir, for the introduction and the opportunity to talk about our work. So I will just begin with a general context of our works. The shoulder is composed, in fact, of two bones, so the humerus and the scapula, and the glenohumeral joint surface on the scapula is called the glenoid. In the case of the LC shoulder, the two bones are well defined, as you can see on this X-ray. But in fact, this is not the case anymore in pathological shoulders. So in fact, this condition leads to pain and a reduced range of motion. And in such a case, non-conforming total shoulder arthroplasty could help to reduce pain and to retrieve a mobility. In fact, this type of arthroplasty consists in replacing the two bones of the glenohumeral joint by two components of the same geometry than the anatomy. So typically, the humeral head is replaced by a sphere, which is in metal and which represents, in fact, the normal, the anatomical humeral head. And the glenoid component is in plastic and is a flat and concave surface, as you can see on the picture. Finally, we call this type of arthroplasty a non-conforming arthroplasty because the glenoid component diameter is larger than the humeral head diameter. And an important parameter is the difference between the radii of curvature between these two components, and it's what we call currently the mismatch. The main advantage of the non-conformity is the better reproduction of LC glenohumeral joint. So previous studies show, in fact, that it better reproduces the term the kinematic. It means that we are the three non-rotations, like abduction, adduction, flexion, extension, and the rotation intern, extern, but also two translations in the inferior, superior, and anterior, posterior directions. So you can see in the picture, it's typically in the X and Y directions. However, the drawbacks of this parameter, of this mismatch, is the main cause of the first complications of NCTSA, namely the glenoid loosening, which in fact is the loss of component fixation in the bones, and the glenoid plastic wear. So you can see in the picture A, we have a wear, in fact, at the inferior part of the component. And on the X-ray, the glenoid component losing is shown, in fact, with the small black lines around the pegs. So if, okay, I can't find my mouse, I'm sorry. The first question about these types of complication and the mechanism for this complication is in fact linked with the translation and the forces. This mechanism has been described by Franklin and it was named the working horse effect. In fact, as he said, the non-conformity allows glenohumeral joint translation, what leads to an eccentric loading on the glenohumeral joint, and the forces is applied on the rim of the glenoid, and this leads in fact to the loss of fixation. This mechanism is also correlated to plastic wear, since more humeral head translations is often associated with an increase in the wear, as it was shown in 1990 by Boyd and collaborators. The problem is that there is no clear consensus regarding the choice of the mismatch. I show you here a table about this specific question. As you can see, the conclusions differ and they recommend different values depending the study. Currently, we know that, or it's accepted that a mismatch between 5 and 10 mm, as proposed by Volch and collaborators, is often recommended. But in fact, this choice stays questionable, since you can see here, to better reproduce the healthy kinematics, we could prefer a 4 mm mismatch. So the question is opened. Then our research question was dedicated to finding an optimum mismatch that would minimize the glenoid loosening and the wear while keeping small humeral head translations. In our study, we chose to define the glenoid loosening risk based on the definition of the working host effect. So we were specifically interested in quantifying two types of parameters. The first one was the humeral head translation, and the second one was the contact mechanism of the prosthetic head on the glenoid component. In fact, the mismatch was declared as minimizing the glenoid loosening risk and wear if it minimized glenohumeral head translation and minimized contact pressure while simultaneously centering the humeral head. And we were able to quantify the position of the humeral head by the contact values. So our objective was to develop a musculoskeletal shoulder model adapted to the NCTSA context, to the arthroplasty context. And we were specifically interested in simulating humeral head translation, as well as integrating prosthetic components to evaluate the contact mechanisms. Our second objective was to quantify the parameters responsible of glenoid loosening and wear, as I described just in the previous slide. So to sum up the translation and the contact of the humeral head on the plastic glenoid component. In this slide, I switch on the method used. So I first explained to you how the initial any-body shoulder model, in fact, that we found on the repository is modeled, and most specifically how the glenohumeral joint constraints are implemented. So first of all, the humeral head translation relative to the glenoid aren't modeled. So in fact, the glenohumeral joint is modeled as a ball and socket joint with only 3 degrees of freedom. So it will be called in the next slide the ball and socket constraint. In addition, contact between bones and or prosthetic components are not considered, and rather glenohumeral joint reaction trajectory is enforced to stay inside the glenoid, and we chose to call this constraint a stability constraint. So in the next 2 slides, I will describe how we adapted the model to the NCTSA context, so by removing these 2 constraints and choosing 2 types of definitions. First, we were interested in adding the translation between the humeral head and the glenoid component, what we were able to model in the basic shoulder model. So for that purpose, we transformed the ball and socket joint into a 5 degrees of freedom joint and managed the translation with the force-dependent kinematic algorithm. Just as a reminder, the previous webcast described in detail this algorithm, so I will not talk about that in details. But quickly, this algorithm simultaneously computes muscle and joint forces as well as joint kinematics, and the computation is based on the quasi-static force equilibrium in the selected degrees of freedom. So in our application, we were specifically interested in the inferior superior direction and in the anterior posterior direction. So our goal was to simulate the soft tissue's influence on the overall glenohumeral stabilization. So we chose to use a nonlinear elastic model for the springs to in fact reproduce the inferior glenohumeral ligament behavior, because in fact we know that this ligament is one of the primary stabilizers for the translation in the inferior superior direction during an arm elevation. And moreover, it's known as a static restraint for the interior subluxation of the humeral head. The second modification to adapt the model was to change the native stability constraint to take prosthetic component contact into account. So we introduced the humeral head and glenoid component as CAD model, and this model in fact are composed of triangle and vertices, and these vertices were used to compute contact forces. A rigid model was used, and the total contact force was calculated as the sum of each contact force, which is described by the FC in the equation. And in fact, the contact force, the total contact force F, corresponds to the glenohumeral joint reaction force. About the simulation, we simulated a basic and easy motion, which in fact it was an elevation in the scapular plane with scapulohumeral region until 120 degrees. And I just remind you that the objective of our study was to evaluate the effect of the mismatch on glenoid loosening risks. So to do so, we tested 5 mismatches proposed by an orthopedic company, and the 3 larger, so the 6.4 mm, 8 mm, and 9.6 mm, was in fact, it corresponds in fact to the recommended values by Walsh and Boileau, so between 5 and 10 millimeters. While the smaller ones, so the 1.4 mm and 3.4 mm, are generally avoided by surgeons. So here are the results. The first parameter we wanted to evaluate was the humeral head translation in the inferior, superior, and anterior, posterior direction. First, a comparison with the literature indicate that our results are of the same order of magnitude for both AP and IS directions. So for the AP, we have something like between 2 and 2.7 millimeters, and in the IS direction, it's about 1.7 millimeter to 2.5 millimeters, depending the mismatch. About the effect of the mismatch on humeral head translation, the first observation is that all recommended mismatches, so between 5 and 10 millimeters, seems to have only a small effect. To reduce the risk of complication, the range of translation has to be minimized, and based on this criteria, the optimum mismatch seems to be the one of 3.4 millimeter. And the last observation is about the 1.4 millimeters, because as you consider, it seems to be out of place. So why did we get some higher translation than for the 3.4 millimeter? In fact, it's pretty strange if we just think to the geometry of the arthroplasty. But in fact, if we have a look on the position of the humeral head on the glenoid component, which is represented on the figure on your right, for the 1.4 millimeter mismatch, the humeral head is applied on the rim of the glenoid. And in fact, the glenoid component doesn't constrain the humeral head anymore. And it's for this reason that we have area translation, because the humeral head is anymore constrained. The second kind of results relates to the contact between prosthetic components. So the center of pressure that I will call COP in the next slide corresponds to the contact position of the humeral head on the glenoid. So globally, we observe that the COP is located in a posterior superior region, and this result, in fact, is in accordance with previous study, and specifically studies which were interested to evaluate and to have a look at the retrieved glenoid component, where we saw that where was situated on this position. Besides, a mismatch has only a small influence on the COP position. Considering contact between the 3D models lead to the computation of glenoid joint reaction force, and in fact extensive studies have focused on evaluating this parameter. Among other in-vivo studies led to the conclusion that this force peaks at 90 degrees of arm elevations. Here you have two studies, one from Poppen in 1978, and the other by Bergman, where they used instrumented implants to measure the glenoid joint reaction forces. And conclusions of the numerical studies, however, do not all converge. In particular, one of the numerical models from Favre and collaborators lead to an increase of the glenoid joint reaction force above 90 degrees, while the others agree with the in-vivo conclusions, so the fact that for above 90 degrees, the glenoid joint reaction forces would decrease. The glenoid joint reaction force calculated in the native antibody folder model, so the one found in the validation of the repository, had the same behavior with a decrease of the glenoid joint reaction force above the 90 degree of arm elevation. Our model, in the opposite, is rather in accordance with the one of Favre and collaborators, and in fact, we think that the main conclusion of this different observations is that below 90 degrees results are of the same order than others, and that we could conclude that we all agree with the values, while it's more questionable above the 90 degrees since we have a very wide range of values for these parameters. As other in vitro studies, we observed that whatever the mismatch is, the contact area increases with the arm elevations, and moreover, it decreases as the mismatch increases. So this is typically, we observe the area shown on your figure on the right, and you calculated the contact area. The contact pressure was then calculated based on joint reaction forces and contact area just by dividing the two parameters, and in fact, except for the 1.4 millimeter mismatch, for the same reason in fact than before, the contact pressure increases with the mismatch. And based on the contact pressure parameter, the optimal mismatch is obtained for the 3.4 millimeter or for the 6.4 millimeters that in fact had the same values for these two mismatches. So we're getting to the end of the webcast, and I'll begin with the contribution of our approach. From a modeling point of view, we adapted the in-vivo shoulder model to NCTSA context, and to do so, in fact, we changed the glenoid joint constraint to simulate small humeral head translations and the contact between humeral head and the glenoid components. Some elements of validation have been shown based on the parameter values from the literature studies. Our study also contributes to improve and, in fact, help orthopedic surgeon and orthopedic surgery. We were, in fact, especially interested in the mismatch effect on the glenoid loosening risk, and this risk was evaluated by quantifying humeral head translation and contact patterns, contact mechanism. So based on that, we could make three recommendations. The first one relates to the fact that there is only a small effect for mismatches between 5 and 10 millimeter. So in fact, from mismatch ratios recommended by the orthopedic companies. The optimal mismatch seems to be defined for the 3.4 millimeter, and it corresponds to a combination of minimal humeral head translation and minimal contact pressures. On the contrary, the critical case was defined as an eccentric humeral head position relative to the glenoid, a maximal humeral head range of translation, and a maximal contact pressure. Based on these values, our results suggest avoiding the 1.4 millimeter mismatch. Some limitations were noted. The first one referred to the deltoid modeling. In fact, above 90 degrees of arm elevation, this method doesn't have a physiological representation. That what is shown on the figure on the right. The problem comes probably from the artificial ray created to work the humeral head, the latter being defined as a circle. So the main consequence is that the anterior deltoid forces are very close to zero, but it's known that the interior fibers are important abductor of the shoulder. What we proposed about that is a modification of the deltoid modeling to improve this aspect, and several approaches could be tested, such as modeling the deltoid as a mesh in which, in fact, each fiber depends on its direct neighbors. The second limitation referred to the input kinematics. So we simulated our arm elevation only to evaluate the adaptation into the in-vivo shoulder model. So it would be now really interesting to introduce more complex movements such as daily living activities. And we know that instrument and prosthetic studies from the literature, as the one from Bergman and collaborators, could be used to describe the kinematic inputs and to validate the implementation. To conclude, just quick words about our future works. The NCTSA model developed during the study is the first step to answer the need expressed by orthopedic surgeons. To adapt the shoulder model to create a numerical tool adapted to non-developer users, because we know that using musculoskeletal model is very complex and surgeons cannot use. And finally, we think that our model could also help to companies to evaluate new design on the biomechanical parameter. In consequence, it's important to improve collaboration between academic and industrial fields. I really thank you for your attention, and if you have any question, you could write on your panel. I will try to answer that, or just contact me by email. I will answer with no problems. Thank you.
Okay, thank you very much, Lauranne. It was a very interesting presentation. I think you showed a lot of interesting results as well. I think we understand that there are some limitations left, especially in a higher abduction angle, but I think in below 90 degrees there was a very good correlation with literature data and some experimental data. And I think it's interesting to see if this model can be applied in the near future, even in clinical environment, or then more likely in implant development. I think that's very interesting to see that. Before we go on to the live questions session, usually this is where I advertise our new webinars, but because this is the end for us for 2014 in webcasts, I want to thank everyone who attended all the webinars in 2014, and we are preparing at the moment new interesting topics for 2015 as well. We are trying to get something in sports, ergonomics, automotive, and of course again in orthopedic area. We don't have fixed dates yet, but I think it's going to start in end of January again. I know that some of you are doing some nice models as well and some nice biomechanic studies as well. If you're interested in ever presenting here as well, doing a webcast for us, please feel free to contact me or anyone from anybody. So my email address is aa@anybodytech.com. Then, yeah, I want to thank you again for joining here. If you have any questions, or if you're interested in contacting us somehow, so we have the homepage anybodytech.com. There you will find a list of events where to find us physically. We're usually going to many conferences. We will also find the dates there. You will find a publication list. So we usually have a list of many publications related to anybody and anybody models. So if you want to have a look there, it's usually categorized by orthopedics, ergonomics, automotive, and so on. So you can find something in there. Also, if it's shoulder, if it's upper extremity or lower extremity or spine related. We have a homepage called anyscript.org. This is the homepage of the community. So that is where we discuss technical things. There's a wiki for technical questions, also a forum for technical questions. I mentioned before there's a YouTube channel. In there we have certain videos, so help demos, tips and tricks, and also all previous webcasts. So you can find previous webcasts there. If you have any other questions, either write me personally, aa@anybodytech.com, or then at inquiry@anybodytech for other issues.